This is going to be a lecture over the problems that we have here for chapter 15. Wanted to go through each one of these so you have an idea as to what to do to solve them. Going to switch on over here, and I've got them numbered 1 through 6. So you can kind of see what it is that we're doing here. So let's take on the old drawing tool here. So the question is up at the top. A new batch of Iridium-192 wire sources has arrived, and its calibration must be checked. So the supplier states the activity in the material was 0.351 millicuries per seed 10 days earlier. What is the expected activity of the Iridium-192 today? Well, in order to be able to generate this, the first thing that we're going to need is going to be lambda. How do we generate lambda? Well, if you look through the lectures that the lecture or the PowerPoint that I had over this, you'll find out that the half-life is going to be equal to, in the lecture, it's going to be 0.693 on the top. I just refer to it as a natural log of 2 divided by lambda. If you rearrange this, you find out that lambda is going to be equal to the natural log of 2 divided by the half-life. Now, also in that same lecture, I have several half-lives listed for several different isotopes, this being one of them. So the half-life here is 73.83 days. Now, as it turns out, lambda is going to end up being the natural log of 2 divided by the half-life, which is 73.83 days. And so if you do the math on that, this is what it turns out to be. So once you know lambda, you're able to determine the activity, because the activity is going to come from the initial activity, which we were given. This is what it was 10 days prior. That's going to be multiplied by the number e, which is raised to a particular exponent, which is minus lambda times the amount of time. So we know what the initial activity is. We know what lambda is because we just computed it. And we know what the time is here in days. So if we put all of this together, which the number of days there, hang on just a second, that should be corrected. I just copied that down. That should not be like that. There we go. So the activity, let's see if I can clear this out. The activity ends up being, go and write it like this, equals A naught E to the minus lambda T. This is the same as saying 0.351 millicuries times E raised to the minus 0.009388 days to the minus 1 power times 10 days. Now what happens here? Well, the days pretty much cancel. And you've got this, which is basically this multiplied by 10. So you end up with 0.351, which, there we go, millicuries times E to the minus 0.09388. And if you multiply all of that out, then this should be the value that you end up with, 0.320 millicuries. So since you're looking at something 10 days later, and this is what it was given to you then, it should be less than that. And that's sort of an informal check that you can make, just to show that the answer, at least in that sense, does make sense. So let's go on here to number 2. What is the radium equivalent of a 25 millicurie source of cesium-137? How do we determine that? Well, again, this comes out of the lecture. So the milligram radium equivalent is going to be equal to the activity of the isotope in millicuries, and that's given to us, times the gamma of this particular isotope divided by the gamma of radium. Now, the gamma of radium is pretty much established here, 8.25 Rankin's squared centimeter divided by the millicurie hour. The gamma of cesium-137 is something that I believe is actually also given in the lecture. So it's 3.28, and the same units apply here. Then we have the activity of the cesium-137, which is this. So by going through and multiplying all of that out, what we get here, let's say, grant myself the ability to be able to write. So we have the milligram radium equivalent is going to be equal to the activity. So we got 25 millicuries times, and then we have the gamma of the isotope, which is 3.28. Now I'm going to go ahead and write these units out here, but I want to show you that these units are going to end up canceling each other. You have Rankins here, you have squared centimeters here, you have millicuries here, you have the hours here. And the reason is that this is just a ratio. They just want to be able to adjust the activity here based on the ratio of what the gamma rate happens to be for each one of these. And if you take 3.28 divided by 8.25 and multiply it by this, you end up with this, and millicuries is going to be your unit because that's the only thing left. Okay. All right, so let's go on to question 3 here. A full strength radium source has an active length of 3 centimeters. So what is the activity of the source in milligrams? Well, in order to be able to figure that out, of course, if we can given the active length, the activity is going to be the strength of the source in mass per length times the length of the source. Now, for a full strength source, if you go back through and you look at the lecture, you find out that's the same as 0.66 times or 0.66 milligrams per centimeter. So if you take that and activity becomes 0.66 milligrams per centimeter, and you multiply that by this, then eventually the centimeters cancels, 0.66 times 3, and you end up with 2 milligrams because that's the only unit that remains. Let's see if I can figure out exactly. The eraser. No, why did I? I get a little clicky sometimes. It's not good. Let's see. Let's try and get rid of it. Okay. All right. So now let's move on. Let's go here. Question number 4. Every year, a new decayed value must be determined for clinical use of the cesium-137 tubes. The decay is always calculated from the original activity assayed value obtained when the source was received. In other words, we verify what the activity was when we got it. One source was received on February 18th, 2003. Which is way out of date if we look at it now. And that value was determined to be 69.5 millicuries. What would be the activity for the source 365 days later? So again, what we're going to be looking at here is we're determining the half-life in order to get to lambda. So the half-life here, if you look that up, it's going to be 30 years. The half-life is going to be equal to the natural log of 2 divided by lambda, or lambda is going to be equal to the natural log of 2 divided by the half-life. So then, let's see if I can get this going. So we're going to have lambda. It's going to be equal to the natural log of 2 divided by the half-life, which in this case is going to be 30 years. It's a little bit over that, but not by much. That's going to end up turning out to be that value. Now, once we have that, then we can determine what the activity will be. And the activity in this particular case is, of course, going to be based on the initial activity, which we had established here. We've got lambda, which was established there. We have the time. So the activity is going to be equal to the initial activity times e to the minus lambda t, which in this case is going to be 69.5 millicuries, t to the minus, and the lambda 0.023105. And that would be, I don't know why I put days there. I'm obviously not thinking here. Let's see. This should be, and let's go to home here. It's not going to give me control. Okay, so let's see. Let's clear the annotation. Maybe that'll help. No, it didn't help. Matter of fact, that put me back. Let's see. I want to take it off of. Anyway, that apparently is just not working. I'm not sure why. That should not read days to the minus 1. That should be years. Let's see if I can actually. Years to the minus 1, and the time there should just be years. That should be canceled out. So you should end up, the activity is equal to 69.5 millicuries times e to the minus 0.023105. Years to the minus 1 times 1 year. Those to cancel. So you end up with A is equal to 69.5 millicuries, D to the minus 0.023105. And if you multiply all of that out, this is what you come up with. All right. So problem 5, 106 millicuries of gold 198 is implanted into a pelvic mass and determine the emitted radiation. So the way you do things like this is first you find the mean life. Again, this is referenced in the lecture. The mean life is going to be the half-life times 1 over the natural log of 2. That, since the natural log of 2 is generally this value, 1 over the natural log of 2 ends up becoming 1.44. Now, the book or the slideshow actually tells you to use 1.44, and that's fine. That'll get you close. But anyway, this is really a more exact value for it. The half-life here is going to be 2.7 days. So the mean life is going to end up being, or the average life, depending on how you want to write it. Is going to be equal to the half-life, which is 2.7 days, multiplied by 1.44, with a few more digits there if you want to, and then that turns out to be 3.9 days. Now, is that our answer? Of course not. What you're trying to figure out is this is going to be the average amount of time that these sources are going to be active. You've got the activity that started, that they were implanted in. So if you take the activity at the implant time and you take the mean life that was given, this is the value that you get when you multiply both of those two together. I think it's a little off from what you actually see because I think the answers are actually posted along with this. But I think the values here are a little bit more exact than what's there. And then finally here at 15 cm from an iridium 192 source, exposure rate is 305 milliroentgens per hour, or 0.305 roentgens per hour. So what is the activity of the source? There's another equation in there that relates the exposure rate to the activity. So we know what the exposure rate is in this particular case. Gamma of iridium 192, closest value that I can find here is 4.8. And again, that's going to be roentgens squared centimeters divided by equal to 15 cm. If you take this particular equation and you reorder things, what you find here is that if I take this equation and rewrite it, which in this case is x dot, that's how be referred, is equal to the gamma, the isotope, times the activity, times 1 over the distance squared. Now, if you want just the activity, you're going to move this variable and this variable over the other side. So in order to do that, if you divide both sides by gamma, then you end up with this divided by that. And then if you multiply both sides by d squared, then you end up with this is equal to d squared, the exposure rate over the gamma. And that's what this is trying to show you right here. So if you plug in the values here, 15 centimeters squared here, the exposure rate of 0.305, and then 4.8 here, this is the value that that I come up with. I know the paper actually gives something that's closer to 15, but this is a methodology I've got and the values that I've got. So this is what the answer turns out to be. So I hope that helps sort of walk you through how to go through some of these problems. And again, always, if you have any questions, you just let me know.